Welcome to a brief explanation of what scientific notation is and why it's useful. So the number I've got displayed on the screen right now is 602 hexillion is how you would say it out loud. And this number, if you remember from chemistry, is the number of particles that are in that package that we call a mole in chemistry. And so it has a lot of uses for us. However, the way that it's written right now is what we call the standard form. And this is how we write most numbers. Standard form. How this is written. And the standard form is just written as a number with no exponents or anything like that. It's just a straight up number. All right. So, and again, we would say this is 602 hexillion. It's a very useful number. However, the way that it's written in standard form is very cumbersome because obviously there's a ton of zeros in here. I had to write out 602 followed by 21 other zeros. And if you imagine displaying this on a computer screen or a calculator screen, some calculators don't have enough digits to actually display this number in its entirety. So for ease of displaying or ease of writing or even ease of calculating, we have a different way to communicate a number like this or to express a number like this. And what we call that is the scientific notation. And what the scientific notation does is it condenses this number down into a little bit more simple of a way to do it or of a way to express it. And there are a few tricks, and we'll talk about that as we go, okay? So basically what we're gonna do is we're gonna pull out all of the quote unquote meaningful numbers here. You'll notice that the 602 hexillion number here has got 602 and then a bunch of zeros following it, okay? So basically what we're gonna do is we're gonna forget about most of those zeros and we're just gonna write 602. So I'll write that down below, 602. Now, so I got rid of most of the zeros, right? I don't wanna get rid of this zero in between the 6 and the 2 because that is communicating to us something a little bit more meaningful than the other zeros. What's communicating to us is the distance in place value between the 6 and the 2. Okay, so we do want to include that, any zeros that are in between our non-zero numbers, but we can get rid of all the other zeros unless they're significant, which we will talk about in a different lesson about significant figures. Okay, but don't worry about that for now. What we're going to do is we're going to write that 602, right? And then to express this in scientific notation, I'm going to put a decimal in here, and that decimal is going to go in a very specific spot. Where it's going to go is directly next to the first number. It's going to go to the right of the first number, and then all other numbers that are significant, that are not zero outside of the non-zero numbers, are going to follow that decimal, okay? So no matter what the number is, this is how we're going to express our decimal portion of the number. We're going to have our first non-zero number followed by a decimal, and then all other non-zero numbers following that decimal. All right. Now, obviously, 6.02 is a very different number than 602 hexillion. So what we need to do is we need to communicate that our number is on the same order of magnitude or the same size as that original number in its standard form. And so how we do that is we multiply times 10 to some exponent. So if we just multiply by 10 itself, what would that do? That would give us a number that is not 6.02. It is instead 6.02 times 10. Obviously, it's 60.2. Obviously, 60.2 is not 602 hexillion, right? So let's scrap that. And instead of multiplying by 10, let's multiply times 10 to the second power. When we do that, we're really taking 6.02 and multiplying times 10 to the second power, which is 100. And 6.02 times 100 would be 602, which is getting us closer to 602 hexillion, but still not there. And you see how multiplying by 10 to some exponent won't change the 602 and their order or relationship to one another, but will change how large our number is. So let's think about what exponent of 10 we need to multiply by to bring this 6.02 back up to the same order of magnitude as 602 hexillion. So ultimately, we want some decimal up here on the 10 so that brings us from 6.02 back to the same order of magnitude as the 602 hexillion. And if we look back at our standard form number, our original expression of 602 hexillion, there is a decimal in here. It's just implicit, right? We didn't write it out because this is such a large number that we don't need to include a decimal. But the decimal really would be at the very end of this number, right? And basically, when we multiply by 10 to some exponent, the 10 to whatever exponent is moving our decimal some number of place values away from the spot where it currently is. So let's figure out how far this decimal point is in the original standard form notation for this number, and figure out where it is relative to where we want to get it, right? Which again is right in between the 6 and the first 0 next to the 2 in our 602 hexillion. So if we start down here at the where our decimal is originally 602 hexillion, we have to move it 1, 2, 3 spots to get to the thousands, another 3, 6 to get to the millions, 9 to get to the billions, 12 to get to the trillions, 15 to get to the quadrillions, 18 to get to the quintillions, and then 21 to get to the hexillions. And then we have 602 hexillion. So to get to that spot again where we want it to be, right next to the 6, we need to move it another 2. So a total of 23 decimal moves to get from where the decimal point is in our standard form notation so that the decimal ends up next to the 6 in our scientific notation. And so since we had to move our decimal 23 times, that means we need to multiply the 6.02 times 10 to the 23rd in order to communicate this same number, 602 hexillion, in scientific notation. So this is how it looks in scientific notation. 602 hexillion would be expressed in scientific notation as 6.02 times 10 to the 23rd. Okay, so let's do the same thing just with the smaller number now. So this number we've got here, again, we've got our standard form. I'm going to call it SF, our standard form right here. And this is 0.000000000667. And this is actually the universal gravitational constant, which we'll use when we start talking about gravity a little bit later on in this course. So we can communicate this again in scientific notation. And again, we would want to for a number like this because this number is so small that it's annoying to write with all of these zeros, right? So again, what we want to do is we want to take our significant digits, in this case 667. So all of the other numbers are just zeros prior to the first 6, right? And we're going to write 667. And we want to put the decimal in the exact same spot as we did it with Avogadro's number, and the exact same spot as we would do with any number expressed in scientific notation, which is always directly next to the right of the very first non-zero number. So we got 6.67, and then we have to multiply times some exponent of 10 in order to bring us back to the size of that original number in its standard form, right? So in this case, unlike with Avogadro's number, we have an explicit decimal point in this number because the number is so small that we had to express it with a decimal point, right? So let's figure out how many times we have to move it to get it to that point in between the first two 6s, which is right there, right? So we'd have to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times to get it over to the spot where we want it to be, right? So 11 decimal moves. In this case, these decimal moves were to the right, whereas with Avogadro's number, we were moving the decimal over to the left. Now, you can, if you wanted to, memorize that one of these gets you a positive exponent, one of them gets you a negative exponent, but I like to think about it just in terms of getting bigger or smaller. So let's first figure out what our exponent's going to be, and then let's figure out when we would employ a negative exponent on our 10 or when we would employ a positive exponent on our 10, okay? So we got 6.67. We know it's going to multiply times 10 to the 11th, right? However, this is a really small number that we were looking at right here, right? And if we multiply times 10 to the 11th, we're actually making a bigger number. So obviously, we don't want to be doing that. We did have 11 moves of our decimal, so we do want an exponent of 11, but actually, this is times 10 to the negative 11th because 10 to the negative 11th will make a smaller number rather than a larger number. So if we express a universal gravitational constant, that 0.000000000667 in scientific notation, then we'll end up with a number that's a little bit easier to say without all those zeros, and that is a little bit easier to write down here, all right? So we end up with 6.67 times 10 to the negative 11th. And again, that's a negative exponent because this is a small number, whereas we would end up with a positive exponent to make the number larger to match a larger number in standard form. So I hope that's useful to you in terms of understanding scientific notation, right? The key points here are that our decimal point for scientific notation is always going to fall in the same spot in the decimal digits prior to our exponent, right? It always should be directly next to the very first non-zero number. And then we're going to multiply that decimal number times 10 to some power, that power being the power that gets us back to the original number in the standard form, right? Because all we're doing when expressing a number in scientific notation is not changing the value of that number. All we're doing is changing the way we're expressing it with the digits we use to represent it. All right, so it should still be the same number in the end, just expressed in that scientific notation form rather than the standard form with no exponents. And that exponent will be positive when we have a large number or negative when we have a small number. So that's how we express numbers in scientific notation. And you guys have a worksheet on practicing this. So give it a go and let me know how it goes.